Hello and welcome to today's lecture on TCP IP. We shall continue our discussion on Internet and Internet working. Here is the outline of today's talk. First, we shall discuss about the relationship between TCP IP and the popular OSI model. Then we shall discuss about various issues related to Internet working, for example, addressing, particularly IP addressing. Then in that context, subnet masking, and also the address resolution protocol, ARP and RARP. And then we shall consider how fragmentation and reassembly is done in IP. And also there are several companion protocols like ICMP and IGMP, which are related to Internet working and used along with the Internet protocol, IP protocol. We shall discuss about them. Then we shall discuss about two protocols, SLEEP and PPP, which are used by home users for connecting their computers to the Internet service provider using IP. And although at present IP version 6 is commonly used, but it has got a number of limitations which can be overcome by the use of IP version 6, but it is yet to become popular. But in this lecture I shall just give an overview of IP version 6. And on completion, the students will be able to explain the relationship between TCP IP and the OSI model. They will be able to explain the different classes of IP addresses, and they will be able to explain the concept of subnetting and subnet masking, and they will be able to explain address resolution protocol and reverse address resolution protocol, ARP and RARP, and they will be able to explain fragmentation and reassembly that is necessary while doing Internet working, and they will be able to explain ICMP and IGMP protocols and how they are used in conjunction with IP protocol. And then we shall discuss, they will be able to explain the SLEEP and PPP protocols, and they will be able to explain how they are used for Internet access by using IP. Then the key features, they will be able to state the key features of IP version 6. As I mentioned in the last lecture, you will require a combination of hardware and software for Internet working, and in the last lecture we have discussed various hardwares like repeaters and hubs, bridge, router, gateways. These are the different hardware that you will require in Internet working, and in today's lecture we shall discuss about the software, particularly one of the two softwares, which is a protocol which is known as TCP IP. And as I mentioned, this acts as a glue to link different types of LAN and WAN to provide Internet, a single integrated network for seamless communication. So TCP IP is essentially a software. It's a set of protocols, and we shall see how what is the relationship between TCP IP and OSI model. Although TCP IP was developed much earlier than OSI model, always we try to map a particular protocol with the OSI model. Let us see what is the relationship between TCP IP and OSI model. As you can see, the TCP IP has got only 4 layers in contrast to 7 layers of OSI model. And for example, the lowest layer is not any specific specific thing can be used here, but which is a combination of physical and data link layer, and one is free to use any type of network like ARPANET, local area network, satellite network, SONET, or they can use simple serial links and like SLEEP and PPP, which provides you the physical and the data link layer. So the physical and data link layer forms one layer in TCP IP. Then comes the there is a layer which is corresponding to IP layer, network layer, which is IP, Internet Protocol, and it has got several other companion protocols like ARP, RARP, ICMP and IGMP, which we shall discuss in this lecture. Then there is a protocol TCP or UDP, which is part of the which can be considered as transport layer protocols. And finally, the session, presentation and application all are not present in TCP IP. There exists a single application layer, and which provides a number of protocols for various applications like STMP for transfer of mail, FTP for transfer of files, Telnet is used for sending mails, and SMTP used for monitoring network, simple network management protocol, and then SNMP, simple network management protocol, is used for management purposes, and TFTP. So these are various application layer protocols which we shall discuss in the next lecture. Then, as I mentioned, there are a number of internetworking issues like addressing, packetizing, fragmentation and reassembly, routing, flow control, error detection and error control, congestion and quality control, security and naming. And particularly all these functionalities are provided by two protocols. One is IP, another is TCP IP. That is why they are paired together to form TCP IP. And particularly IP provides a unreliable, connectionless, best effort datagram delivery service. So if we want reliability, then we have to use TCP, and TCP provides reliable, efficient and cost effective end-to-end delivery of data. So these two together gives you host to host communication in a reliable manner. And particularly the IP will provide these functionalities like addressing, packetizing, fragmentation and reassembly and routing. So these are the functionalities which will be provided by IP protocol, which we shall discuss in this lecture. First, let us focus on addressing. In TCP IP you will encounter 3 different types of addresses. As you know, if you want to send a letter, you have to write the address of the destination, and then put the letter in the letter box. Similarly, if you want to send any information, you have to know the address of the destination where you want to deliver. And in TCP IP you will encounter 3 different types of addresses. We have already seen the physical layer address, which is also known as MAC address, medium access control address, and for example for Ethernet it is of 48 bits. And then IP has got provides you internet address, which is or IP address in short, which is 32 bits. On the other hand, the TCP will require some addressing, and that is 16-bit address, and it is known as port address. So you will encounter 3 different types of addresses in TCP IP. We have already discussed about the physical address or MAC address. For example, the physical address comprises 48 bits, and here is the format of that. So apart from 46-bit addresses, the first 2 bits decides whether it is for individual address or it is group address, it is, that means you can use for unicast whenever you have to use the individual address, and whenever you are sending to a group of people, then you have to use the multicast address. And there is another bit U or U versus L, UIL, which gives you that global or universal address, or it can be a local administered address. So when it is I, it corresponds to L, when it is 0, it corresponds to U. So we see that whenever broadcasting has to be done, all the bits are to be 1. Each station on this network receives an access frame. So with the help of this MAC address, you can do unicasting, that means 1 to 1, broadcasting 1 to all, or multicasting 1 to a group of people, 3 types of delivery by using MAC address over a single network or LAN. However, we are interested in internetworking, and obviously we would like to communicate between a number of LANs or LAN, WAN and so on. So in such a case, we have to use internet address, and internet address, as I mentioned, comprises 32 bit, and this 32 bit has got 3 different fields. First one is known as provides the class or type. Actually the addresses are divided in 5 classes, A, B, C, D, E, which is specified by first few bits. For example, if the first bit is 0, then it is a class B address. If the first bit is 1 and second bit is 0, then it is class B address. If the first bit and second bit both are 1 and third bit is 0, then it is class C address. And if first 3 bits are 1 and fourth bit is 0, then it is class D address. And if all the 4 bits are 1, first 4 bits are 1, then it is class E address. So we can see, apart from this class, the remaining part is divided in 2 fields. One is known as network ID, another is host ID. And as you can see, in different classes, particularly A, B and C, the size of net ID and host ID are different. In case of class A, net ID comprises only 7 bits and host ID comprises 32 bits, 24 bits. So here it is 8, I mean that there are 8 bit of net ID including 0, most significant bit, and host ID comprises 24 bits. On the other hand, in class B, you have got 10 followed by 14 bits of net ID, and you have got 16 bit of host ID. On the other hand, in class C, the first 3 bits are 110 and remaining 21 bits are net ID and 8 bits are host ID. And 110 and remaining bits, here you have got the multicast address, that means remaining 28 bits provides you the multicast address. And class C is 1111, this is reserved for user, not presently in use. There are 2 ways you can write an IP address, in binary form, where you have got a sequence of 1s and 0s. For convenience, as you can see, it has been divided in 8 octets, in 4 octets. 4 octets, each of 8 bits. Then another notation which is commonly used, which is known as dotted decimal notation. Dotted decimal notation, as you can see, each octet comprises consists of 8 bits, and these 8 bits are represented, instead of binary, it is represented decimal form. So the range of number that can be in each field varies from 0 to 255, which can be represented by 8 bit. And so by using 4 octets with the help of their decimal values and each separated by a dot, this is known as dotted decimal notation. And using this dotted decimal notation, the range of host addresses for different classes are given here. For example, in case of class 1, it will be from 1000 to 127.255 5.255.255. In case of class B, it varies from 128.0.0.0 to 191.255.255.255 .255. So you see the class B whether a address corresponds to class A or class B can be found out by looking at the first field of the dotted decimal notation or first decimal number. So if it is in between 128 to 199, it belongs to class B. If it is from 1 to 127, it is class A, and then class C from 192 to 233, that belongs to class 3, and then class D is from 244 to 239, and from then class E is 240 to 247. So you see this is the range of numbers that is being used by here there is a mistake, actually it should be 234, not 234, not 244. So it has to be 234.0.0.0 to 239, and on the other hand it is from 240 to 247. This is class E. Of course it is not in use. Now you may be wondering why 0 is not here in class A. So for that purpose there are some special IP addresses apart from those general cases. For example, if the address is all 0, it means this host. This is commonly used at the time of booting. Then if the address is being sent to a host on this network, not a different network, then first 10 bits can be 0, remaining can be the address of the host or host ID. Or if it is a broadcast on this network, you are sending to all the computers or systems on the network, that then it can be all 1. So you have to exclude all 0 and all 1 whenever you count the number of addresses possible. On the other hand, broadcast on a distant network, then you will give the network ID by using 10 bits, and remaining fields can be all 1. You are trying to broadcast to a distant network, and net ID can be 10 bits. And whenever you want to do loop back, you want to receive on the same host, then it can be 127, and this field can be anything, remaining bits can be anything. So these are some of the special IP addresses. Now you may be asking, whenever an IP address is being used, how a particular network receives a particular packet which is meant for that network. This is done with the help of a technique known as masking. As you can see, this is the IP address, and this within this router there is a that router has to filter out packets corresponding to this network. So it does not bother about the host ID, it only bothers about the net ID. So what is being done, some kind of AND operation is performed with the net ID part. That means it is the mask is 255.255.0.0. that means all bits are 1. So 1 1 1 1 1 1 1 1 1 1 1 1 1 1 1, then remaining bits are 0. This is masked, this is ANDed with this 144.16.5.210 to filter out the net ID. So here is the 144.16.0, then this is being looked into the table of the router, and if there is a matching, then it receives it, otherwise it is not allowed to pass through the router. So if this matches, then it sends it to this network. It has been found that this particular technique uses essentially two levels of addressing, two hierarchical levels by using net ID and host ID. So it uses two levels of hierarchy, and unfortunately the number of hosts and networks varies as you choose a particular class. For example, if a class A addressing is used, as we know, 8-bit is in this case, as you can see, only 8-bit is used for net ID, remaining is host ID. So if class A address is taken, then if the number of hosts in a particular network is small, then a large number of addresses are wasted. On the other hand, if class B address is taken, a good number of hosts is good number of addresses are wasted, because usually in a single network you don't have 64 K of addresses. So with the help of 16 bit you can have 64 K addresses, but you may not have 64 K addresses. On the other hand, if you take class C address, the total number of address available is only 254. So excluding that broadcast and all 0 and all 1, so if you can have only 256 addresses. So to begin with, if you start with C, after some time it may not be adequate, so you have to use apply for another address. So this can be avoided, this problem can be avoided by introducing an intermediate level of hierarchy in the form of subnetting. So what is being done in subnetting? The address is divided into in 3 parts: the net ID, subnet ID and the host ID, as it is shown here. So suppose in this particular address, say 144.16.5.210, let us assume we are obviously it is clear that we are using class B addressing. So the network address is represented by 144.16 then 00. This is the network address. However, what can be done? You can use within the network 8-bit is used as subnet address, and remaining 8-bit is used as the host ID, identification of the host, right. So ID of so by doing this, what you can do to the external world, it is the same network as you can see here, but locally you can have a number of subnets, and which can be done by using a masking, a special type of masking known as subnet masking. So instead of 16 ones, you will use 24 ones in this particular case, so that as an address comes, by masking, by ending with 24 ones, you get an address like 144.16.5.0, and each is sent to different subnets. As you can see, by this router can send all the hosts to all the hosts corresponding to the subnet 144.16.6.0. So with the help of subnet mask of 255.255.255.0, that means you are using 24-bit ones in the first part. So in this way you can do subnet masking, and you can have a number of subnets within a single network. So to the outside world, essentially it is a network of 144.16.0.0, but within the network you can have different subnets. For example, different departments within IIT can have a separate subnet. On the other hand, to the outside world, it can be a single network having address 144.16. So this is the concept of subnet masking that is being used. And now comes the question of another protocol that is known as address resolution protocol. As you know, for delivering a packet to a host or a router within a network in the physical layer, I mean in the data link layer, it is necessary to know the network MAC address or physical address, sometime we call it. So if a particular host or a router does not know the physical address of the destination device, then how it will know? That is provided with the help of ARP, address resolution protocol, in a dynamic mapper. So it does dynamic mapping approach for finding the physical address for a known IP address. That means the IP address of the destination is known, but for delivering the packet it is necessary to use the physical address. So that physical address can be obtained by using this ARP protocol, and it is done in 2 steps. ARP request is a broadcast. So ARP, the user sends a request ARP to send a broadcast message to all the stations in the network. As you can see, suppose A is the host who is looking for the destination physical address. So it sends a packet, that means the ARP sends a packet on this network, and it is a broadcast message. So it is received by all the host in that network. Then the host which is actually host requesting the mapping, that means ARP reply, that means the concerned host which matches with the destination IP address sends the reply. So here in this case it is a unicast, that means it is one to one, it sends the packet to the host A providing the physical address, and for that purpose some kind of special type of frame is being used. So this is the ARP packet, and ARP packet is encapsulated in the MAC frame. As you can see, this is the typical Ethernet frame, preamble, then SFD, that synchronization frame detection, then data, then destination address, source address. These are all 6-byte addresses, 48-bit addresses. Then the type, in this case the type specifies that it is a ARP protocol, and here as you can see there is field corresponding to the hardware address, that is the physical address, as well as the protocol address, that is your IP address. So 6 bytes and 4 bytes, and target hardware address and target protocol address. So initially the target hardware address is given all 0, and whenever it is returned the proper target address is provided. So this is how, with the help of ARP, a particular station can know about the physical address if a station knows about the IP address. The reverse one operation is being performed by RAP. In case of RAP, the physical address is known but IP address is not known. For example, this can happen in a diskless workstation. At the time of booting, it should know the the IP address, although it knows its physical address. So to know the IP address, it sends a request to the server, and server sends a reply with the IP address. But presently RARP is becoming gradually getting obsolete. It is being replaced by another protocol which is known as DHCP. We shall discuss about it later on. Now let us consider the second issue, that is packetizing. Packetizing means the data has to be sent in the form of a frame, and the packet which is received from upper layers which is used by the internet protocol to frame a datagram or frame. So the datagram, as you can see, includes a header comprising a number of fields, and the data is included. Apart from data, it adds a header. So the header has got a number of fields which is explained here. For example, it has got the version field which is represented by 4 bit. For example, presently the IP protocol is IP version 4 that is being used. So if you use IP version 6, then that has to be mentioned in this version field. Then header length 4 bits says about the length of the header expressed as the number of 32-bit words. So maximum size is 5 and minimum size is 5 and maximum is 15. So so the header length is specified with the help of this field. Then you have got the total length of the frame, length in bytes of the datagram including headers, maximum datagram size. So you can see the IP frame or datagram can be of 64 536 bytes, or which is the maximum size of the frame datagram. And the service type field, the service type field is actually used for allows packet to be assigned a priority. So router can use this field to route packets, but however it is not universally used. Then there are other fields. Time to live, it prevents a packet from traveling forever in a loop. That sender sends a value and that is decremented at each hop. If it reaches 0, packets are discarded. We have already discussed about that that flooding, and flooding can be restricted by controlling the number of hops. So this is one, this field can be used for that purpose. Then the protocol field is there, which defines the higher level protocol that uses the services of the IP layer. So the packets will be coming from different higher level protocols, so it has to do some kind of multiplexing with the help of this protocol field as it is shown here. So the protocol field allows the some kind of multiplexing. As you can see, the packets are coming from a number of upper layers like ICMP, TCP, IGMP, UDP, OSPF. So these are the different higher level protocols, and it receives a packet and sends it to the next lower level. And obviously the next lower level, I mean whenever it reaches the destination, you have to do the demultiplexing. By looking at the protocol field, it again delivers it to the proper protocol, ICMP or TDP, TCP or IGMP or UDP or OSP. So for the purpose of this multiplexing and demultiplexing, this field is necessary, this protocol field. Then the source IP address is necessary, 32 bits destination IP address, and this identification, flags and fragment fields, these fields are used for the purpose of fragmentation. So let us consider the fragmentation and reassembly, how it is being performed in the IP layer. Why fragmentation is necessary? As you know, each network imposes a limit on maximum size known as maximum transfer unit or MTU of a packet because of various reasons. There may be various reasons for restricting the size of a packet. As you know, if the packet size is very large, then the probability of error in the packet increases. So to reduce the probability of error of a packet, the size is restricted, or different standards use a different size of packets or frames. As you have seen, IP allows you 60, that means 64 kilobyte. On the other hand, the Ethernet uses 1500 bytes, and in this way different standards uses different size packets. Now in the internetworking, when we do internetworking, packets are originating from different networks and they have to pass through different types of networks. Now suppose a network receives a packet which is bigger than it can handle. So how this problem can be tackled? There are two ways of handling it. One approach is to prevent the problem to occur in the first place. That means the source takes care of that. The source is requested to send packets of smaller size, I mean the minimum size, so that the maximum size allowed by any network in the path from source to destination. So this is one approach which you may call prevention. The second approach is to deal with this problem is to use fragmentation. What can be done? This gateway is allowed to break packets up into fragments and send each fragment as a separate IP packet. So this is the second approach which is commonly used in most of the cases to have more flexibility. However, fragmentation is very easy, breaking a packet, breaking anything is very easy, but putting them together is very difficult. Even a child knows about it. So similar situation arises in reassembly. Fragmentation can be done, but reassembly is a more difficult problem, and how it can be done, let us see. So fragmentation, the reassembly is performed in IP with the help of three fields: identification, flags and fragmentation. But before I do that, let me explain in general how reassembly can be done. Reassembly can be done in can be performed by using two different approaches. First one is known as transparent fragmentation. In this case, the gateway router which receives the packet breaks it up as it passes through the network with the maximum size. Then at it reaches the exit gateway or exit router, it is reassembled. So when it comes out of the network as it was received, so within the network it is fragmented, but as it comes out, it comes as the original packet. it is reassembled by the exit router. So, in this case the problem is each and every packet has to be routed through the same exit gateway. So, as it passes through different networks, it is transparent to the source as well as the destination. So, destination receives a reassembled packet as it has been sent by the source. So, this is known as transparent fragmentation as it is done by the ATM network. So, of course, in ATM network instead of fragmentation they used a different term known as segmentation. So, the transparent fragmentation is being done. On the other hand, in case of Internet protocol or IP, non-transparent fragmentation is done. Here, as the packet passes through different networks, it is broken down or fragmented based on depending on the maximum size allowed within a network. For example, here the gateway has divided into where the packet has entered has divided fragmented the original frame into a number of frames, and the exit router does not do anything. So, it can be exited through different paths. So, the sender sends one packet, and through this network when it comes out 3 packets are going towards the destination, and as it enters another network it is further fragmented into each packet is fragmented into 2. So, 6 IP packets are generated by the network 2. So, it is the responsibility of the route to the destination node to do the reassembly. That is why it is called non-transparent fragmentation, which is done by the IP protocol by using 3 fields: identification, flags and fragmentation offset field. Identification part is a 16-bit field that identifies a datagram originating from the source host. So, this identification parts remains unaltered as it goes, as it is fragmented, and there are 3 flags, 3 flag bits. The first bit is not used, it is reserved. The second bit is do not fragment field, and the last bit is more fragment field. That means whether this has to be fragmented or more fragmented, that is being specified here. That means whenever with the help of these 2 bits one can specify whether fragmentation has to be done or not to be done. Then the fragmentation offset is specified the different fields, I mean how with relation to the original data. Here explained with the help of a packet which is of 4800 bytes, which is divided into 3 fragments. As you can see, each will have a header and it is divided into 3 fragments. So, here it is divided into 0 to 1599, then 1600 to 3199 and 3199 to 4799. So, these are the 3 packets. Now, as we have seen, the maximum size is 64 kilobytes, which cannot be represented by 13 bits. That is why it is expressed in terms of 8 bytes. So, this 1600 is divided by 8 to get an offset of 200, and 200 is written in that offset field. Similarly, here it is 3200, which is the offset from the with respect to the beginning, which is divided by 8 to go get 400, and 400 is written of course in binary in 13 bits in that fragmentation offset field. So, this is how it is fragmented, and these fragmented packets as it reaches the destination node will be able to do the reassembly by using this information. So, it uses the non-transparent fragmentation technique as I have explained here. Then there are other fields, options fields. This can be used to provide more functionality to the IP diagram, and there is a checksum field which is of 16 bits. Checksum is calculated the way I have already explained earlier while discussing error detection. The header, it is only done for the header part. So, header is treated as 16-bit integers. The integers are all added using 1's complement arithmetic. Then the 1's complement of the final sum is taken as the checksum, and if the checksum does not match, then the frame is discarded. Now, let us discuss about ICMP, a companion protocol used along with IP protocol. We have seen that IP is a best effort unreliable protocol. So, if an error occurs, if a frame gets corrupted, then or if it is not delivered, the source will not know about it. So, since IP has no error control mechanism, there is no flow control mechanism, ICMP has been used, which is ICMP stands for Internet Control Message Protocol, which has been designed to compensate for these deficiencies. That means to make it more, since it is unreliable one, but the source should know what is happening, what has happened to a particular packet, that is being provided with the help of this IPMP. And IPMP can send a number of messages, or it can do the query. How it happens, let me explain. It can send different types of messages. For example, destination unreachable. A packet is sent and a router is not able to deliver the packet. So, in such a case, it will, although the packet is not delivered, a ICMP packet is generated informing the source that the destination, that the packet that was sent has not reached the destination, or time exceeded. So, a packet is discarded as the time is exceeded. In such a case also an ICMP frame is sent to the source to inform that a packet has been discarded because it was out of time. Then source quench. As we know, the IP protocol does not provide flow control or congestion control, are not supported by IP. So, in such a case, source quench somehow provides you the facility for provides the functionality of flow or congestion control. So, whenever a particular packet is discarded because of congestion, then a source quench packet is sent to the source informing that the packet has been discarded, and moreover there is congestion is existing in the network. Then parameter problem, whenever the frame reaches with incorrect field, in such a case parameter problem arises, which is also informed to the source. Then redirect message is necessary whenever a router receives a packet, but it is not able to, it is not meant for that particular router. So, it redirects it to towards the proper destination. At the same time, it informs the source about the redirections. So, these are the various messages that is being supported by ICMP, and also different kind of queries can be performed. For example, echo request and reply. In this case, a station can send a request to another's destination station to reply to know whether the destination station is live, working or not working. Similarly, timestamp request and reply. In this case, a source can send a frame to the destination, and destination will also use the timestamp and reply, and by this the delay can be, round trip delay can be estimated, or this can be also used to synchronize two clocks, the source clock and the destination clock. So, for synchronization of two clocks or for measurement of delay, this can be used. Then address mask request, that means a particular station may not know about the subnet mask. So, that can be queried and it can get the reply. And for that purpose, there are a number of message formats which are shown here. For example, destination unreachable, time exceeded, source quench, then timestamp request, timestamp reply, and so on, which are not, let us not discuss in detail these message formats. Then comes the question of routing. As we know, there are three different types of routing: unicasting, multicasting and broadcasting. Unicasting is a one-to-one communication, and there are two different types of protocol. One is known as interior and another is known as exterior protocol. As you know, the network is divided into in a number of autonomous systems. So, the communication within the autonomous systems can be performed with the help of two protocols known as routing information protocol RIP and open shortest fast protocol OSPF. A routing information protocol is based on distance vector routing, and open shortest path protocol is based on link state routing, which we have already discussed in detail while discussing the routing techniques. And whenever the routing has to be done outside the autonomous systems, say inter autonomous system routing has to be done. For that purpose you require a different type of protocol. For example, border gateway protocol or BGP, which is based on path vector routing is used, provided to do this routing. So, these are the different protocols are used by IP. However, it has to also support multicasting. As we know that class D address is having more than 250 million addresses for the purpose of multicasting. So, multicasting is used to send message to a group of users which is supported by IP, and so you have to use some suitable protocol for that purpose. However, to keep track of different groups, a special protocol is used which is known as IGMP or Internet Group Message Protocol. Do not get confused with the routing protocol. IGMP is not a multicasting routing protocol, but it helps multicast routing. So, what it does, it has been designed to help multicast router to identify host in a LAN environment. So, and IGMP uses three types of messages like query message, membership report and lib report, and it operates in a somewhat similar to ICMP. We have already discussed how ICMP works. In a somewhat similar manner IGMP works and does the group message protocol, does the function of multicasting. We have discussed about different types of LANs, WANs which are used in the internet working. Now, as I said, a home user suppose wants to use TCP IP. How you can do? By using serial link it can be done, and that can be done by using serial line IP or SLIP. So, in this case station sends raw IP packets over serial line with special flag byte 0xC0, and of course, if it appears in the IP frame, then you have to use that technique as you have done for in the case of you have to use suitable technique so that this is not repeated in the IP frame, and then it performs. However, it has got a number of limitations. It does not use error detection and correction. So, error detection correction is not supported by SLIP protocol. Then IP addresses should be known in advance, that means source and destination address should be known, and it supports only IP protocol. Other protocols which are used in internet working is not supported, and also it does not use any authentication, and also there is no standard for SLIP. So, different manufacturers have developed different versions of SLIPs which are not compatible to each other. So, these are the limitations, and how it is used is shown here. Suppose this is the home user which uses a dial-up telephone line, or it can use lease line as well to get internet service from an internet service provider. So, he can use SLIP protocol to, with the help of modems, it does the it can set up a serial link, then it can use the SLIP protocol to communicate between the host and the router in the internet service provider premises to communicate, to send IP frames, between these two agents. So, to overcome the limitations of PPP, point to point, to overcome the limitations of SLIP, a protocol has been introduced which is known as PPP, point to point, and it performs error detection, it supports multiple protocols, it allows IP addresses to be negotiated. So, it means the IP addresses need not be known beforehand, and it permits authentication. So, it makes it reliable compared to SLIP, and this PPP protocol uses HDLC framing, and as we have seen in the previous case, it does bit stuffing whenever this is not being done. 0xC0 appears in the IP packet. Similarly, here also bit stuffing can be done whenever flag bit appears in the data field. And apart from using this HDLC framing, it uses, as I said, it performs it sets up the link with the help of that link control protocol LCP. So, it uses for bringing up, testing and negotiating options, and also for bringing down. As you can see, in the initial case it can be in idle state, then it goes to when the link is established, it goes to established state when the carrier is detected, and if it fails it comes back to idle. So, this is the flow diagram for PPP protocol. Then it does the authentication, and if it fails it goes to the terminate state, and if the authentication is successful it goes to the communication protocol by using the network control protocol is used to perform the configuration purpose and to perform communication between the two devices. And for that purpose the different packets the LCP, PAP and CHAP packets are encapsulated in that HDLC frame which we have already mentioned. For example, this protocol field specifies what type of packet it is, whether it is LCP or PAP or CHAP. LCP stands for link control protocol, PAP stands for password authentication protocol, and CHAP stands for challenge handshake authentication protocol. And the payload has got different codes for different functions, and ID it holds for the value of match with a request and reply, and length and the information which is extra information needed for some type of packets. So, this is how the different packets can be put in the payload of the HDLC frame. I think our discussion will not be complete if I do not mention about IP version 6. We have seen that IP version 4, which is now very popular, has got a number of limitations which is being overcome in IP version 6, and these are the key features of IP version 6. So, it uses 128-bit address instead of 32-bit address. So, 32-bit address is gradually becoming insufficient, and it uses more flexible header format compared to IP version 4, and basic header followed by extended header. So, it is used in two levels. It performs resource allocation options which were not provided in IP version 4. It provides, there is provision for new or future protocol options, and it supports for security, there is facility for authentication, and in this case the fragmentation is done at source instead of performing that non-transparent fragmentation. So, these are the key features of IP version 6. Now, it is time to give you the review questions. First question is why do you need ARP protocol? Second question is what is the purpose of dotted decimal representation? Give dotted decimal representation of the IP address given here. Then third question is how is masking related to subnetting? Then fourth question is what limitations SLIP protocol are overcome in PPP protocol? Fifth question is what are the key features of IP version 6? Now, it is time to give you the answer to the questions of lecture number 33. First question was, why do you need internetworking? Answer is, as stations connected to different LANs and WANs want to communicate with each other, it is necessary to provide this facility. Internetworking creates a single virtual network over which all stations in different network can communicate seamlessly and transparently. So that is the purpose of internetworking. Second question was, why a repeater is called level 1 relay? Answer is, a repeater operates in the physical layer. Data received on one of its ports is relayed to the remaining port bit by bit without looking at the contents. That is why a repeater is called level 1 relay. Third question was, what is bridge? How it operates in the internet networking scenario? A bridge operates in the data link layer. It looks into various fields of a frame to take various actions. For example, it looks at the destination address field so that it can forward the frame to the port where the destination station is connected. It also looks at the frame check sequence field to check error in the received frame, if any. A bridge helps to create a network having different collision domains, as we have discussed in detail. Fourth question was, what limitation of transparent bridge protocol is overcome by the source routing protocol? Transparent bridge protocol uses spanning tree algorithm where a unique path is used to communicate between two stations. As a consequence, it does not make use of the other path, leading to lesser utilization of the network resources. This problem is overcome in source routing algorithm. Fifth question was, what limitations of a bridge are overcome by a router? Answer is, a router overcomes the following limitations of a bridge: linking of two dissimilar networks, routing data selectively and efficiently, enforcement of security, vulnerability to broadcast storms. So these are the advantages of router over bridge. So with this we come to the end of today's lecture. So there will be another lecture on TCP IP where I shall mainly focus on TCP. Thank you.